This is lecture 2.5, transformations day 1. This should be review from algebra 2. So ideally, nothing is new here. When in doubt, you can always make a t-table when we're graphing the parent functions. The first thing we're going to talk about is shifts. This is one way to write the standard form of any kind of function. You might see k on the other side as well. So some of you guys might have seen it written like this, with k on the other side. These rules apply for this form, where k is with y. So h controls shift horizontally, so left and right. K controls shifts up and down. If you use the form at the very top of the page, negative k or negative h means we're moving up and to the right, and then positive k or h means we're moving down and to the left. It's kind of the opposite of what you would think for both h and k. If you use the form at the bottom, it just switches for k. So up is plus k and down is minus k. So we want to graph the parent function and then also the shift. So I'm going to do these in different colors. On your homework, I ask that you guys do one with a solid line and one with a dotted line. So usually I'll graph the parent function with a dotted line and then the transformed function with a solid line. So y is equal to x squared. This is our parent function. This is a parabola that faces upwards. So we move right 1, up 1, right 2, up 4. 5, 6, 7, 8, 9. We can fit right 3, up 9, and then we'll go left as well to graph those transformed points. So I'm using shortcuts for graphing these parent functions. These are things we did in algebra 2. All right. Our parent function, I did that in a dashed line. If you've got multiple colors at home, you can graph them in different colors instead. I'm going to do the transform function then in blue. So ask yourself, where are we taking the parent function x minus 2 squared minus 5? So we're taking the parent function x squared. We are going to shift it to the right 2. And then that minus 5 means we're going down 5. So we're going to take all of those points from the green parent function. We're going to shift each of those points right 2 and down 5. And with some video magic, we've got all of those parent function points shifted right 2, down 5. Now, we didn't stretch anything. There wasn't a value in front that represents a, the stretch there. So the shape stays the same. We just picked the graph of x squared up and moved it right 2, down 5. So you guys try number 2, graph the absolute value parent function and then its transformations. Pause the video and come back when you guys have finished that and check your answers. Okay, so the parent function here is graphed in red, and then when we graph the transformed function in blue, if you identify those transformations correctly, that plus 3 on the inside of the function, inside of the function is the horizontal transformation left or right. That is left 3, so we moved all of the points left 3, and then up 4. K is on the outside, that controls that vertical transformation. So stretches are a different type of transformation. They actually change the shape of our graphs, and we always determine the stretch by that constant sitting in front of our function. So whatever we're multiplying the whole function by, that is going to be our stretch, and it's a vertical stretch by a factor of a is what we call it. We call it a shrink if a is less than 1, and that actually would cause our graph to get wider. So we want to graph these 3 things. I'm going to do it again in colors so you guys can see. We've got the parent function first, x squared, so that's just an upward facing parabola. So right 1, up 1, right 2, up 4, right 3, up 9, 10, 11, 12, 13, 14, 15, 16. I think we can make it 25. 17, 18, 19, 20, 21, 22, 23, 24, 25. Perfect. Okay, so we can do up to 5 squared, and then I'm going to transform the points on the left hand side. And then again, I'm going to graph the parent function with a dotted line. All right, so next up, we need to graph the stretch, 1/3 x squared. So this is actually a shrink by a third. how we would identify that. And that means we're taking all of the y values of our parent function and we're multiplying them by 1/3. So every y value we multiply by 1/3 and then plot a new point. So I'm going to walk you guys through that. 0, 0, the y value there is 0. 0 times 1/3 is still 0. So the origin stays the same. Next we go to 1, 1. So the y value there is 1. If we multiply that by 1/3, our new y value is 1/3. The x values don't change, only the y values on these vertical stretches and shrinks. Okay, so 4 times 1/3 is 4/3. So that's our next point. And then 9 times 1/3 is 3. Then we have 16 times 1/3, which is going to be 5 1/3. And then lastly, 25 times 1/3, that's our last y value, is going to be 8 1/3. All right, and all we have to do is just mirror those points across the y-axis. So we can do that a little bit more quickly, less math to have to worry about there. And our vertical shrink then becomes this wider graph, right? Shrinks are a little bit wider than the parent function. Last one here, we've got the opposite. We've got a vertical stretch. So we're stretching by 2. That means that we're going to multiply all of the y values of the parent function by 2, and the x values still stay the same because it's a vertical stretch here. So 1 times 2 is 2. 4 times 2 is 8. 9 times 2 is 18. And then the other points are going to fall off the graph. So as long as we've got 5 points for a parabola, we're good to go. I'm just going to reflect these over the y-axis. And our vertical shrink is going to be more narrow than our parent function. So that's how we know we've done this correctly. Okay, so 3 graphs. The green is our parent function. That's the one in the dotted line. We've got a vertical shrink by 1/3. That's our wider graph. And then our vertical stretch by 2 is the more narrow one. Give number 4 a try, pause the video, graph those, the parent function and then the stretch, and then come back and check your answer. We've got the parent function, the absolute value of x in red, and then the stretch is a stretch of 5. So that's where we see the blue graph more narrow than the original parent function. It's going to have a steeper slope essentially on both sides of the line. So the next type of transformation we're going to talk about today are the flips. So there's 2. We can flip over the x and we can flip over the y, and we have to remember which one belongs with which if we're looking at the equation algebraically. So think about this. If we've got a point sitting on the x-axis, and I take that point and I make the x value negative. If I turn the x value negative, that is going to reflect over the y-axis. So when the x value becomes negative, it becomes a flip over the y-axis. Now think about the other thing. If I have a y value, which would be our function values, right? Those look like that. If we take that y value or that function value and we make it negative, that's when we see a flip over the x. So anytime we've got an equation that takes x and replaces x with a negative x, we see a flip over the y-axis. Anytime we see our entire function turn negative, or those y values become negative, we have a flip over the x-axis. That's how I remember it. Okay, so here we go. The graph of y is equal to negative f of x is identical to our parent function, except it's been flipped over the x-axis. We took all of those y values, we made them negative. We're flipping over the x-axis in that case. The graph of y is equal to f of negative x is identical to our parent function, except for we've taken all of the x values, made them negative. This is where we see the flip over the y-axis. By the way, there is a spot to write all of this on page 9 of the student note packet. So in the pink section, page 9, at the very top box, there's a place for all of that information. So we're going to practice some flips here. The first is going to be graphing this x minus 5 squared. So this is going to become our parent function, and then from there we will start flipping depending on where we see the negatives in the next two examples. So x minus 5 squared, that's our parent function x squared moved to the right 5. So I'm just going to take the original parent function points. We'll start with the vertex, and we're moving it to the right 5. That minus 5 on the inside is that horizontal translation. Okay, no stretches, no movement up or down, so we just have a standard parabola from there. I'm going to quickly sketch in some of those points. That is enough to get us a solid looking parabola. So that's what we're starting with, and I'm going to treat that now as our parent function as we go about flipping in the next two examples. So I'm going to graph the next in blue. We've got a negative on the outside. So anytime we've got a negative on the outside, that means our whole function, or the y values of our function, become negative. That's our flip over the x-axis. So I'm going to take all of those points that we just plotted in green, and we're just going to flip them over the x-axis. So anything sitting on the x-axis is going to stay, but then we're going to go right 2, down 4, right 3, from the vertex down 9. We just flipped all of those points over the x-axis. When we're looking at parabolas also, just think back to what you know about parabolas in Algebra 2. Anytime we had negative x squared, it just went from an upward-facing parabola to a downward-facing parabola. So that's another way you could remember it's a flip over the x-axis. Okay, in the next case, we've got x being transformed. So we're taking x, we're making it negative x. That means that we're flipping the green function over the y-axis this time. So I'm going to take all of those points from that original green function, we're going to flip them over the y-axis. So the y values become negative here. The x values stay the same. Missed the 4 there. Okay, fix that. And there we go. Okay, it's a little tricky on an iPad. So that is our flip across the y-axis. Pause the video, try this one. Remember that the square root function has a domain restriction, so think about that as you guys go. Pause the video, come back, check your work after you're done. Final answers for number 6 should look like that. We've got a flip over the x in blue and then a flip over the y in purple. Now this is a question that I get every year, and the question is this: why do we have this? We can't take the square root of a negative number, right? That's the rule. So what happens when we have this case is if you look at the graph in purple, which is the representation of this, we actually have a domain restriction in the opposite direction. So this is for all the values of x that are strictly less than or equal to 0 there, which is why we see all of the values for this purple function are only in that interval. So we can do that as long as we restrict the domain, and that's what we see in the graph there, which is why it's only to the left of the origin. Okay, so for the homework problems that look like this, you don't have to do 4 separate graphs. You can do all of the graphs on one grid, but you should show all of the steps. So just note that. So number 7, we want to find the function that is finally graphed after we follow all of these transformations. So we're going to do each step in a separate graph, and do this in the notes, but on your homework you can do each step on one grid. So the first thing we're going to do is we're going to graph the parent function. So this is just the absolute value of x. And I can just drop a line here. Looks like that. And then the next step is to shift this down 3 units. So I'm going to take my absolute value function and we're just going to shift all these points down 3. So that vertex goes down 3, and then the rest of those points also. Now I want to write the function as well because the question is asking us to find the function. So if I took my absolute value and I shifted down 3, that would look like this. The absolute value of x minus 3. Okay, step 3, we want to reflect about the x-axis. So that means we're going to take every single one of those points in step 2, we're going to flip them over the x-axis. So if I take all those points and flip them over the x-axis, that means our vertex now is up at positive 3. And then we see that the points where we cross the x-axis in step 2 stay the same. And I want to make sure we represent that as an equation as well. So when we reflect about the x-axis, what happened? Well, we took all of the y values and we made them negative. We took the whole function from step 2 and we made it negative. So how does that look as an equation? Well, we're going to take everything we did in step 2 and we make it negative. So the simplified version of that looks like this, right? And that plus 3 now, we see that movement up 3 from the vertex. All right, so then last step here, we are going to shift everything left 2. So I'm going to take this function from step 3, we're going to move everything to the left 2. That's what the graph looks like. The last thing we need to do is we need to represent that in the equation. So movement to the left 2 occurs inside of the function. If we're moving to the left 2, we're going to represent it as a plus 2 in the equation. And then that plus 3 stays there as well. So y is equal to negative absolute value of x plus 2 plus 3. That's our final answer, final step there. We made it to the last example I'm going to work through with you guys. Number 8, we've got the situation. We are told that the x-intercepts of the graph of our function are negative 3 and 2. So I'm going to sketch that, just like really roughly. Drop an x and a y axis, and we know that the x-intercepts are negative 3 and positive 2. Right? Obviously, this is not drawn to scale either. That's all we know, that our function crosses the x-axis at negative 3 and 2. The first question we're asked is, what are the x-intercepts of the graph of y is equal to f of x plus 1? So let's think about what we're doing here. We're taking every point on our parent function and we're moving it to the left 1. So in part A, if I took those x-intercepts, moved them to the left 1, our new x-intercepts are going to be negative 4 and positive 1. We just shifted everything to the left 1. Okay. We can represent those with ordered pairs as well. They look like that. There we have it. Step 2 asks us, what are the x-intercepts of the graph of y is equal to f of x minus 3? So what are we doing with that transformation? Well, minus 3 means we're moving the original x-intercepts to the right 3. So start with those original x-intercepts, move them to the right 3, and what are we left with? Well, we're left with 0, 0, because negative 3 plus 3 is 0. And then we're also left with 5, 0. 2 plus 3 is 5. Okay, what are the x-intercepts of the graph of 3 times f of x? Well, this is a vertical stretch. Stretches are not going to change the values of our intercepts. The reason is these are original intercepts, negative 3, 0, 2, 0. When we're talking about vertical stretches, we are multiplying the y values. But if you look at the y values of our original intercepts, they're 0. 0 times anything stays 0. So our intercepts, our x-intercepts, stay the same here. Last problem, what are the x-intercepts of the graph of f of negative x? So what are we doing here? Well, we are taking all of the x values and we're making the x values negative. In other words, we are flipping over the y-axis. So take all those points, our original x-intercepts, and flip them over the y-axis. We get our new x-intercepts. Those are going to be -2, 0, and +3, 0. Last problem is yours. Pause the video, give number 9 a try. Number 9 on page 10 of your student note packet. Try those and then come back and check your answers when you're done. All right, if you guys had questions on how to do number 9, because it is a little tricky, I'll walk you through it. If not, you can just fast forward and check your answers at the very end. So we know one thing about this function, and that is it is increasing on the interval -2 to 7. So again, I'm going to sketch something here. Let's say this is -2 and this is 7. And for the sake of it, I'm just going to draw a function that is increasing on that interval. I don't know what anything else looks like, but I know that between -2 and 7 on the x-axis, our function has a positive slope. So we're going to start with that. The next question is this. Over what interval, then, is the graph of f of x plus 3 increasing? So what are we doing when we apply this transformation? Well, we're taking all of the points of our original parent function, and we're moving them to the left 3 spaces. So that is going to take our interval, -2, 7, and we're just going to shift everything left 3. So what can we say about the interval where our function is increasing now? Well, our new function is going to be increasing on the interval -5 to 4. We just take the interval -2 to 7 and shift all of those values to the left 3. Next part, what can we say for certain about the graph of y is equal to -f of x? Well, what are we doing when we apply that negative there? We are flipping this graph. Think about over which axis. We're taking all the y values, we're making them negative, so we're flipping over the x-axis here. So if I were to flip this line that I had drawn over the x-axis, what is it going to look like? Something like that. What can we say for certain about that interval? Well, that means on the interval, -2 to 7, I should write the word interval here. The function is decreasing. That's what we know for certain. Last one, what can we say for certain about the graph of y is equal to f of -x? Well, again, what are we doing here? We're taking all the x values, we're making them negative. So this is a flip over the y-axis. So go back to the original line that I drew in blue here. If I flip all of those points over the y-axis, what is that going to look like? Well, I've got to extend this graph here all the way out to -7 and +2. If I flip all the points on the blue line over the y-axis, it's going to look something like this. Okay, where this point transforms into that point. So what can we say for certain about that graph? Well, we know it's decreasing because the slope of that line is negative. But we also have an interval change. So it's decreasing on the interval, -7 to +2. We switched the values of the original interval. All right, that is it for this section. We will continue transformations in the next lecture.